Okay, welcome to my video presentation. My name is Phua, and first of all, I would like to express my gratitude to the panels, professors, doctors, and also everyone who are watching this video. And today, I'm going to do a presentation about my final undergraduate project entitled Quality Inspection Using Machine Vision System. And this is basically an overview about my presentation. So what is a machine vision? Machine vision is the automatic extraction of information from the digital images. In a machine vision system, there are some basic components which include a lighting system to provide illumination, a camera to capture the image, a processor and image processing software, and of course, an inspected part. The machine vision system has wide variety of application, and one of the application is quality inspection. So why is machine vision system so important in quality inspection? This is because nowadays, due to the rise of IR 4.0 and also enormous scale of mass production manufacturing industries, the companies have to inspect more product at higher speed, higher accuracy, and also higher quality standard in order to become more competitive. And by looking at the traditional inspection method, you can see that the human inspector is doing the manual checking by using their naked eyes, which have a lot of limitations such as imprecision of eyesight and also slow in process. So machine vision will become a more cost-effective method and reliable to provide a better quality products because it can inspect at higher speed, higher accuracy, and also higher repeatability. So in this project, my objective is to establish a workable machine vision system for product quality inspection, which can inspect the diameter of surface geometry of manufactured product. And these are basically the scope of my project. So since my machine vision system is going to inspect the circle diameter of product, therefore, a circle detection method is required. And the circle detection method that I use is half circle transform, which is also known as circular half transform, CHT. So the half circle transform is using the concept of accumulator matrix and also voting process. So for each of the xy points in the original space, a circle is defined in the half parameter space. Accumulator matrix is then used for tracking the intersection point. And in the parameter space, the voting number of points which the circle passing will increase by 1. And in the end, the local maxima point is determined, which indicate the center of the original circle. And the reason why I'm choosing the half circle transform is because it can detect circles even though in imperfect images. And the function is also readily available in the OpenCV library. So these are some application examples of the half circle transform. We can see that the CHT method can be used to detect holes on PCB board and also measure hole diameter of water pump and also detect iris features in the face recognition. So these are the parameters required to be defined for the half circle transform function. And besides, there are some critical parameters that needed to be tuned well to minimize the false circle detection as shown in this slide. So this is the methodology flowchart on how I construct this project. And first, for the hardware use, HDD base plate and Malaysian coins are used as the target workpiece for inspection. This is because both objects have circular features for inspection and they are considered as a mass production part. Next, for the lighting system, I have chosen the ring lighting because it can provide a uniform spread of illumination. The processor used is a Raspberry Pi 4 Model B, and also the camera used is a Raspberry Pi 5 megapixels IR camera module with an adjustable focal length. So this is the hardware setup of the machine vision system. You can see that a double layer plastic rack is used to place all the components, and besides, I also designed a light holder by using the SolidWorks and also fabricate it using 3D printer to fix the position of ring LED light and also the camera. So this is an overall setup of the machine vision system, and we can see that the LED light can be powered up by using the power bank. And these are basically the software used for the implementation of the machine vision system. Next, so how is the circle diameter of the target workpiece being detected by the system? So these are the image processing flow. First, the image is captured by using the Raspberry Pi camera module. And then, if the workpiece have too complicated features, for example like the HDD base plate, we will apply the ROI method to extract the inspected region. So we can see that first, we will determine the X and Y coordinates by clicking the specific point in this created program. And then we will use the coordinates to crop out the specific inspected region as shown in the image. And this is to reduce the surrounding noise. And then we will convert it to the grayscale image so that the half circle transform can work well. And we will also carry out the canny edge detection method. And this is to maximize the edge detection and also minimize the surrounding noise to improve the performance of the detection. Finally, we will apply the half circle transform function on the image to inspect the circle. And for information, the original result from the half circle transform actually will show the detected diameter in pixels form. So, in order to convert the result into millimeter form, we need to multiply with the calibration factor. So how can we get the calibration factor? We need to first perform a calibration process. So we will inspect a reference workpiece with a known diameter in the same image, and then only we can calculate the calibration factor by dividing the actual diameter with the inspected diameter in a pixel form. A simple GUI app was created to ease the inspection process. So this is the GUI of the machine vision system that I've made. So you can see that if I click the capture button, the image will be captured and shown in the display window. Then after I click the inspect button, the circle will be inspected and the output image with the inspected diameter will be shown. So this is an example of the inspection on the third version of 20 cents coin. So from the result, we can observe that the output has showed an error of 2.91%. And this is another example of HDD baseplate inspection. You can see that the HDD baseplate has too many complicated features on it. So as mentioned previously, if we didn't apply the ROI method, false circle detection will occur. So based on the correct circle detection, we can see that a small inspection error of 3.36% still occur. So in order to study about the inspection errors occurred in our machine vision system, 3 inspection test experiments were carried out. The first experiment is regarding the inspection of different height of circles. And based on the past researches done by others, normally they use one reference object for the calibration process to calculate the calibration factor for other objects in the same image. But I think that the calibration factor shouldn't be the same. This is because if the inspected circle is higher or nearer to the camera lens, the diameter detected by the CHD is supposed to have a bigger value. So in this experiment, the aim is to find the relationship between the height of inspected circle and also the calibration factor. So we can see that in this experiment, the system was slightly modified to detect the calibration factor of the 20 cents coin by using the formula shown, and then the height of the 20 cents coin was varied by stacking the 10 cents coin at below. And the 10 cents coin was added one by one until there is a total number of 10 coins stacking at below. So we can see that 5 calibration factor readings are recorded for each different height, and then the average value are taken. And then the tabulated result was converted into a line graph, and based on the line graph, we can see that there is a linear trend. The calibration factor decreases linearly with the height of the inspected circle. Besides, we also obtain a generated trendline equation which can be used to calculate the calibration factor. Coming to the second experiment is regarding the inspection of different coins. And the experiments were divided into 2 sets, which different methods to obtain the calibration factor were used. And the first method is using the previous calibration process by taking the 20 cents coin as reference object for calibration. And the second method is using the generated equation, where the x value will be substituted by the coin thickness or the height of circle. And then the diameter of different coins are inspected and the inspection error is calculated. And we can see the result was then converted into a bar chart, and based on the bar chart, we can see that most of the coins showed lower percentage of inspection error in set 2 as compared to set 1. So this means that the generated equation is a better way to calculate the calibration factor, since it is faster and more accurate, which is less inspection error as compared to the old calibration process. And for the third experiment is regarding the inspection of HDD base plate. 3 circles with different sizes were chosen for diameter inspection. In this experiment, the calibration factor was calculated by using the generated equation previously, and the remaining procedures are similar with the previous experiment. So from the result, we can observe that higher percentage of inspection errors occurs at smaller diameter of circle, and this may be due to the sensitivity of pixels. And this is because the inspected diameter result from the system always show a deviation of up to plus minus 5 pixels. Therefore, the deviation will have a larger effect and result in a higher percentage of inspection error if the circle is very small. Hence, smaller diameter of circle should be inspected by zooming in the image or reducing the distance between the camera and also the inspected circle in order to reduce the inspection error. Okay, so in the conclusion, the objective has been well achieved. A workable machine vision system was successfully established, and based on the inspection test, almost all inspection errors are less than 5%, which means that the accuracy of the system is around 95%. However, my system still show an inconsistency of detected diameter values even though the position of workpiece and also the experimental conditions remain constant throughout the inspection. So for my recommendation, further study on illumination and quality of image captured by the Raspberry Pi processor can be carried out in the future to solve this issue. And that's all for my presentation. Thank you.